Welcome back, chemistry fans. We are going to work on our homework dealing with the equilibrium part 2. And this time we're dealing with something that gets a little bit more complex called Le Chatelier's principle and ice tables. So let's jump into this and see if we can knock this out briefly, make it as painless as possible. Okay, so, I got to shift this to this problem. Here we are. So let's make it where you can actually read it. Okay, so we've got this reaction. We've got nitrogen and hydrogen making ammonia, and this is the Haber process, and it gives off some energy in the process as well. It's at equilibrium. So what we want to figure out is, well, what happens if we just increase this amount right here, if just the hydrogen is increased? Well, according to Le Chatelier's principle, it will try to get rid of stress. It will shift to the other side where you've added extra. So which direction is this going to flip? What's going to happen to the equilibrium? It's going to shift to the right, because it's going to try and get rid of this excess material. So just imagine you have this balance, and if you've added some weight to the one side, that balance is going to now shift. So it's going to try and get itself back to being equal. So it's going to move some of that material to the right side. So that's how we envision this. Now, what happens if I do the opposite? What if I remove some material? Well, now in this balanced scenario, we actually have the exact same scenario. Instead of us having extra, what we have now is a scenario where, where we have less over here and we have more over here. So nature is going to try and fill that hole. So again, it's going to shift back to the right to try and get itself balanced, because right now there's fewer of the NH3, so it needs to make more, so it's going to shift to the right. Okay, well, what happens if you increase the temperature? Well, the temperature can be viewed as this heat. So we've got excess that's on the right side, so we've got to try and get rid of that. So it is going to shift back to the left. Now, the last one deals with your understanding of how there is a relationship between pressure and amounts. So the more moles of gases you have, the more space it will take up. So on the right, we should see that there are 4 moles of gases. On the left, on the right side, there are 2. So the left has 4, the right side has 2. So if I decrease the pressure, in other words, we are going to make this a smaller container. We're going to squeeze it together. Well, nature is going to shift towards the side where it can relieve some of that pressure and get itself back to stability. So it is again going to shift to the right, because this is where we have smaller areas. So if you had a balloon and we had a smaller, and we had, let's make that a better looking balloon. And if we had then a smaller balloon, well, it would be easier to fit 2 moles in, because you have squished, you've put your hands around this one and you've squished this balloon to make it smaller. So it will fit easier whenever we only have 2 moles of gas than 4. All right, last question on here is dealing with something called the ice tables. And the ice tables are set up as following. You set it up with ICE, where I stands for initial, change, and equilibrium. So we have these 3 stations, and then we're going to set up just as we see it in the reaction. So we're going to have the 2 NO2s. We will have, we don't need the equilibrium sign. We will have 2 NOs, and we will have O2. And what we need to see is that we are only given the initial amount of this. What we also have on the side over here is KEQ equals 1.2 times 10 to the negative 5. Well, what we are looking for, our goal, is to solve for these 3 values down here. Well, we don't have enough information, but we do know how it's going to proceed in this reaction. We know for a fact that at the start, we have 0. We don't have any of the products. That's just by definition of this reaction. If you start with some material as a reactant, you have no products unless they tell you as such. Now the change comes about. The reactants are going to lose material to make the products. How much material are they going to lose? They're going to lose 2x because of this coefficient. It's going to lose 2 times whatever amount it chooses to lose. And the same is going to be true for then my product. It's going to gain 2 times as much, whereas the oxygen is just going to stay as 1 mole because it only has a 1 in front. Well, now what we can do is we can sum together the initial and change. So I have 0.5 minus 2x, I have plus 2x, and I have x. Here's the nice thing. This value right here is inconsequential. It does not matter because the amount of change, because this is a weak acid, it's not going to change that much. So it's going to stay pretty close to 0.5, and you will see that whenever we solve for our final answer. So what we're going to do now is we're going to set this up as a KEQ type of problem. KEQ is equal to products over reactants. My products, I have NO squared times O2 divided by NO2 squared. Now we have our equilibrium values that we can substitute in. So I have 2x squared times x divided by 0.5 squared equal to 1.2 times 10 to the negative 5, because that's what my equilibrium constant told me. So now we've just got some algebra math that we're going to try and solve here. So let's solve for one of these x's. So 1.2 times 10 to the negative 5 times 0.5 squared. So I've got 3 times 10 to the negative 6. 3 times 10 to the negative 6 is equal to, now we combine all these x's together. So 2x squared is 4x squared times x. That means this is 4x to the cube. Now, how do I get rid of that to solve for the x by itself? We're going to divide both sides by 4. So 3 divided by 4 is 0.75. So I've got 0.75 times 10 to the negative 6 equals x cubed. Well, how do we get rid of a cubed? Well, we do the cube root of both sides. So if we do the cube root of both sides, this will equal x. So in your calculator, you're going to have to figure out a way, and I will try and show you how to do this. You're going to have to use the math function and then go down to step 4. So math function, it'll do a cube root of 0.75 e to the negative 6, and we get 0.0091. So notice it's not going to change. This is how much would have been lost from the 0.5, which is why we were able to get rid of that 2x, because it's not going to change that much. But this is the value now of my x, and if we double it, that's going to be the value of my 2x. So let's put this in here and let's solve. So I have my equilibrium concentration for the NO2 is going to be equal to 0.5 minus 2 times 0.0091. Didn't change that much, 0.4818. That's not much of a change. For my NO value, and this is the second portion of the equilibrium here, it's going to be equal to 2 times x. Well, 2 times 0.0091 is 0.0182. And then finally, the O2 concentration is just equal to x, 0.0091. So those are my 3 answers that you are heading towards. I know there's a lot of steps. It's called an ICE table. It is one of the more complex problems, but they all solve the same way. You just have to remember the pattern. So thank you very much. We'll talk to you again soon. Bye-bye.